Hi everyone, thank you for joining me today for this session. The session is about Windows kernel drivers, and basically I'd like to show you how to write a simple kernel driver. Even though it is going to be fairly simple, it's still going to be useful. So I'll start by briefly introducing what we're going to do, and then we'll just kick it off because there's a lot to accomplish in this 1 hour or something in order to build a driver, and also it means building a client, because the client will give the driver some instruction as to what to do. And I'll describe the driver we'll be building momentarily. So a little bit about myself, as introduced by Anna. I've written a few books. I have a few courses on Pentester Academy and Pluralsight. I'm also a co-founder of training at trainsec.net, which offers courses just like writing a driver, for example, and there's a big course on that called the Windows Kernel Programming, and other very interesting courses that you might want to check out. Other than that, you can just Google stuff about me. All right, so here's the idea. What we want to do is to give you a brief overview of what kernel drivers look like, how they get loaded, how they're used by the operating system and by clients, and then we'll see how to build a relatively simple but useful driver that would allow us to access any process in its entirety. So we'll be able to access any process, including protected processes that normally don't allow access from user mode, even if you have administrative capabilities. So this is going to be pretty fast talk, just to give you the sense of what is going on, but feel free to ask questions while I'm talking. I'll try to answer them as best I can. So we'll start by giving you a brief introduction to the world of kernel drivers and how they're interacting with other parts of a Windows system. We'll see how to invoke drivers from a user mode client, and we'll switch to the driver side of things and look at the driver entry, which is the main function of a driver, and then talk about the main components of drivers, which are device objects, symbolic links, and how to handle requests. So that's the basic idea. Let's get going. So in general, we have this Windows thing where we have user mode and kernel mode parts. The kernel mode is where the kernel is, and also all these kernel drivers, one of which we'd like to write it today. So first we have client applications. This could be just normal processes like, say, Notepad, or various Windows services, and then want to do stuff with the I/O system. They want to talk to devices. This could be files in the file system, but could also be other kinds of devices like hardware devices or even virtual devices. And so the I/O system is comprised of several components. The main one, which is probably the most well-known, is the I/O manager. The purpose of the I/O manager is to handle the standard requests such as read, write, create, things like that. And then we have also other managers which are outside the scope of this talk, which handle other stuff which is definitely important in the Windows system, such as the plug-and-play manager, which is handling plug-and-play stuff, that is identifying in some magical way the hardware connected to the system and loading the appropriate drivers, for example. There's also the power manager, which handles power-related requests. And these are out of scope for this talk, but we'll focus on the I/O manager. And then what happens that once we get a request, say, coming from user mode, for example, to open a file or handle to a device, then the I/O manager is the one that's going to contact the correct driver that's supposed to be handling that kind of device based on some kind of name, as we'll see very soon, which is known as a symbolic link, which is a way to identify or to locate a particular device. That could be a file in the file system, but could be something completely different. For some cases, we have file system drivers. These are the one handling file system requests, such as NTFS, which is a file system driver. And then it will call a lower layer driver, such as a disk driver, to perform the actual access to the various sectors on the disk. So drivers are really the cornerstone of the kernel in the sense that they perform all the connection or communication between the operating system and the hardware, the devices connected to the system. You can't really do anything without the driver. So the fact, for example, that you can hear my voice and see my screen and I can move my mouse and something useful happens means that we have appropriate drivers on my system that allow these devices to work. Otherwise, you won't be able to hear me or anything like that, because you need these kernel drivers, which can be written by Microsoft, but also by third parties. In fact, that's the only official way to insert kernel code into the Windows kernel, by writing a kernel driver. So this is how this looks from a very high-level perspective. What we want to do here is to write a driver that does something useful. It will not interact with any hardware, but will still do something useful because it will have kernel powers. In the kernel world, you have access to everything. In user mode, you have very limited access. So we want to be in that position where we have access to everything. And so that's where our power from the driver side is coming from. So if you think about normal applications, say Notepad, and you use file open to open a file, for example. And obviously, the thing is that to open an actual file, it can't be done from user mode. The only capable entity has to be running in kernel mode, some kind of driver like NTFS. And so there must be some way to reach the kernel from user mode. Now, the way this is done is that the user mode application calls some Windows API. In the case of Notepad, it will call something like read file. Before that, it will actually call a create file function to open a handle to the initial file. And that call, just like read file or any other call really, will go to the kernel in several stages. One of them is being implemented by one of these DLLs known as subsystem DLLs, like kernel 32. And despite the name, this DLL, in fact, is in user mode. And it's one of those that is implementing the documented Windows API, the one you can find in the official Microsoft documentation. And this DLL implements the read file function or the create file function in a way that, in fact, invokes another function, which is known as a native API or a system call, such as NT-read file in the case of read file or NT-create file in the case of create file. And this goes into this very important low-level DLL called NT-DLL, which is the lowest layer of user mode code, which is still in user mode. And the purpose of this DLL for this particular purpose is to make the quantum leap, the transition into the kernel. And it does so by placing a number into the AX register. I'm referring here to Intel AMD architectures, but it works in a similar fashion for ARM64 architecture, just using a different register, and then using a machine instruction, which is syscall_x64, to make the quantum leap into the kernel. So the processor changes modes to kernel mode. It's still the same thread, and then reaches a function called the system service dispatcher, whose purpose is to dispatch the appropriate call, to call the actual API on the kernel side of things. So we have, in the example of read file, we have NT-read file. That's one of these functions. So the NT-read file in user mode and kernel mode look exactly the same. They have exactly the same parameters. But in user mode, it's just a trampoline, something that makes us jump into the kernel. On the kernel side of things, NT-read file is implemented by the IO manager, which actually does something useful. In this case, it builds a data structure that we'll see called the IO request packet, or IRP, whose purpose is to encapsulate any kind of request. So all the details of the request, such as the buffer provided by the user, the size of the buffer, control codes, whatever that may be, is bundled within that IRP. And then that IRP is sent to the appropriate driver for handling. This is where the IO system says, okay, I'm done with that, just send the request, and I'm going to wait until you tell me that the request is done, and then some result will be reported to the client. So these things are happening all the time, not just for IO, but for many other APIs. In fact, anything that means something in Windows has to be performed by the kernel. This is done using this system calls mechanism. Using IO APIs is no different in that respect, but we'll focus on that. We'll focus on what happens with these IRPs and these kinds of things, but just know that this is a generic mechanism. It's not specific to IO stuff. So when we're talking about kernel drivers, what is a kernel driver? Is a kernel driver a process? Is a kernel driver a thread? And the answer is no and no. A kernel driver is just a bunch of functions. You can think of that as a DLL that is being mapped to the kernel address space instead of a user mode address space. So it's just a bunch of functions being called by the kernel at the appropriate time. and these functions always run in kernel mode. And one of the effects of that is that it uses the kernel mode stack of a thread. If you're familiar with Windows, every user mode thread actually has two stacks. One of them is in user space and the other one is in kernel space. I won't get into the details of why that is needed, but regardless, the kernel stack is a small one. It's about 24 kilobytes on x64. That's a fairly small stack, which means that if you go beyond that stack, you'll likely crash the system. So you don't want to allocate big structures on the stack. If you need something big, you should allocate that dynamically. And so we have this sys file, which is part of image space, of the kernel address space. And one of the things that we get when writing a kernel driver, just like the well-known, perhaps American hero films like to say, with great power comes great responsibility, which means that since you have the ultimate power, the power of the kernel, anything bad you might be doing, you'll simply crash the system. And we'll get the very infamous blue screen of death. And the blue screen is not really a form of punishment, which might seem like that initially. It's actually a protection mechanism, because if you continue running when something bad has happened, it might cause Windows to delete important files or not to be able to restart again. So it's best to stop everything right here, right now. That's why the blue screen exists. That's part of the parcel of when writing kernel code. Now, how does a driver get invoked? Usually it's invoked by client code with functions like read file, write file, and device IO control. And don't let the word file here confuse you. File here, in fact, is short for file object, which is the abstraction used by Windows to contact devices. And these devices could be files in the file system, that's one particular case, but could be other devices, physical or virtual. So the term file here is not really about the file system, it's about the file object, which is the abstraction Windows uses to talk to devices. So in most cases, drivers get invoked by clients, usually in user mode, but don't have to be in user mode really. In some other cases, the driver might be registering for various notifications, and then it will be called by the kernel. But we'll focus on the first case, which is easier to see, at least in this session. So essentially what happens when a driver loads, it has a main function that's going to run, and that function is going to export various other functions telling the kernel, hey, if someone calls read, here's my callback. If someone calls write, here's my callback. So essentially what the driver does, it tells the kernel of the stuff that it supports, and then it's going to be called whenever that kind of stuff is actually happening. And we'll see that. Okay, so how do we access devices? So before we do that, let's just jump right into Visual Studio and start writing some code for a client application. In fact, we'll start with the client because it's just easier to start with what the client expects, and then we'll see how the driver implements that so that these expectations are satisfied. So I'm using Visual Studio 2022 here, but any version will actually do. I'm using a console C++ application here to get started. I'm going to call that, let's put that in dev temp here. I'm going to call that list DLLs. The purpose of this application will be to list the list of DLLs in a particular process. And so the thing is that we might be able to do that without the help of a driver for many processes where we might have enough access. But for certain processes, we might not have enough power, and this is where we'd like to invoke the driver. So I'm going to start by doing things in the user mode way to see if we can do that for many processes without any issues, but then for certain processes, like protected processes, this will not work. So I'm going to add include for windows.h. I'm also going to add include for stdio.h to have access to the simple printf function, things like that. And we can begin our simple application here. So the first thing I want to do is to grab parameters from the command line, because I would like to ask the user to provide a process ID to look inside it. And so if the number of parameters is too small, we can say, here's our usage for this application, use list DLLs here and provide the process ID. So if that is not the case, we're going to just exit the application. Now that we have one parameter, we're going to grab it. I'm going to use the simple a to I function to grab the process ID here from the first argument after the actual path to the executable. And so the way to work with that, the way to list DLLs in a process would be first to open a handle powerful enough to the process in question. And the way to do that is to use the function open process. I'm going to do that. Here's open process, and the important point here is to provide the correct access mask that I'd like, the correct power that I need in order for me to be able to list DLLs. And so for that, we need something like process VM read and process query information. How do I know that? We'll see the API I'm going to be using very soon. And if you look at the documentation for that API, it will say that if you want that to work, you have to have that kind of handle with at least this access mask available. And here's the process ID that we received from the command line. If that doesn't work, we get a null handle, we'll want to utilize the driver. Maybe the driver will be able to open a handle to the process in question. If that does work, then we can go ahead and just do the listing. So let's call a helper function called listDLLs and provide a header to the process. Otherwise, we can just say we have an error and that's about it. We can do something simple like that. So let's implement listDLLs here and see if we can work with certain processes without any particular issues. So I'm going to use listDLLs here. I'm going to accept the handle to the process. That's going to be my function. I probably should return something that indicates a failure. So let's just do that, return a simple Boolean. And what I want to do here is to call the function enum process modules. It is another function from the Windows API. However, it is defined in a different header called PSAPI, or the process status API. And enum process modules allows us to enumerate a bunch of modules in a process, assuming we have powerful enough handle. And that's exactly where that access mask comes in. It has to be that, at the very least, for this function to have a chance of succeeding. So we provide the handle to the process, and then we need to get back an array of handles to these modules. So we're going to just define something like 1024 modules at most. That's going to be good enough for this simple demonstration. We can provide the size of the buffer we provide here. We get back the actual number that we need in order for this actually to work. Because maybe we have more than 1024 modules in the particular process. So in this case, I'm just going to look at the Boolean here. If it's false, then it means something went wrong. I'm going to just exit. Once we have that, we can go ahead and look at the number of modules we actually have, which is going to be needed, divided by the size of each module, because it returns the actual number of bytes. So this is the actual number that we have. And then we can go ahead and loop around until we get to count. And then I'm going to use something like get a module base name to have something to display, not just the address of the module in the process address space, but also its base name, that is the DLL name or the executable name. So we can provide a handle to the process, the handle to the module here, and we're going to get the base name as an array of characters. So we can just define something that's going to be probably big enough. And I'm going to do that and provide the size of the buffer in characters. So it's going to be a count of name, which is a simple macro, just calculates the number of elements in this array, which is just 256 in this example. So if that works, I can go ahead and display the results. So the first thing I want to do is to display the address of that module into the process address space, and then the name itself. So we're going to have the HI here, and then also name. That's basically it. We can return true, indicating everything is fine. So now we can test it. I mean, it should work for normal processes that are not too protected. So I've compiled that by doing a build solution here. Then I'm going to go ahead and open a command window here, although we can do that from Visual Studio as well. Let's just open a command window. So here's a command window. Let's go to x64 debug here. So here we have the list DLL's application. You can see that it needs some kind of process ID. So let's provide it with one of those. So let's take something like Explorer here that has an ID 2304. Let's go with that. So 2304. And you can see we get a list of DLLs into this that reside in this particular process. Not very difficult to do once you know the APIs that you want to call. But then let's try something else. Maybe we can try a different process. Say something like CSRSS. CSRSS is a protected process. We have a couple of those. So here's an ID 1132. Let's go with that. 1132. And you can see it fails. In fact, it fails because of an access denied. I can even prove that by showing here the actual error returned by the function getLastError here, which returns the last error occurring in some API call, which is the most common case. So if you go back here after rebuilding that and trying this again, you can see that error is number 5. And you might be familiar with 5 as being access denied. So we don't have enough access to this particular process. And instead, we want to utilize the driver now to be able to actually access that information. Maybe the driver is able to open a handle to that process. Of course, it could also fail because of a different reason. Maybe the process ID is just garbage process ID. It's not really a process at all. But assuming it is a process, we'd like the driver to be able to open a successful handle to that. Okay, so that's kind of where we're starting with. So now we need to talk to the driver, and the question is, how do we do that from the client perspective first? And the way to do that is by using the function createFile. And again, the name createFile is misleading. It's not really about files in the file system. CreateFile is short for createFileObject. And the file object is an abstraction that, as I mentioned already, is able to talk to devices where files in the file system is just one particular case, but there could be any other cases that we can build. And the file name, which is the first parameter to createFile, is not really a file name. It's actually a symbolic link. And a symbolic link is kind of like a shortcut that points to a different device or some kind of device that we're interested in. And in order for the parser to understand that we're talking about a custom device and not really the file system, because the file system does get a special treatment by the createFile API, we need to prefix the name with these two backslashes, a dot and a backslash, and then provide a symbolic link name. Let me show you a quick example of that. So we can use a tool called WinObj from sysinternals. Here's that tool. And there's a directory here called the global2 question marks. And this is, in fact, a directory that shows all these symbolic links that are available and are valid values to the createFile function. So you can see things here like C:. In fact, C: is not really special. You might think that C: is a very special thing, but in fact, it is not. It is just a symbolic link pointing to an actual device object, which is device hard disk volume 3 on my system. And same goes for other drives like D:, which points to some other kind of device, which is a different directory in the object manager namespace. By the way, these directories are not in the file system. These are directories in memory, just a way to group a bunch of objects as in one sort of outreaching or some kind of directory or a container, so to speak. And so you can see that some of these symbolic links look nice, like D:, and you might find things like display1, things like that. But then there are some others which look much uglier. And the reason for that is something I don't have time in this particular session to explain. But regardless, all these strings here are valid values to the createFile function, and they have a chance of succeeding. Of course, they might fail because of security concerns, but at least they are valid parameters of the createFile function to be able to access a particular device by specifying that prefix of 2 backslashes, a dot, and a backslash. So this is what we'll have to do. So we need to call the createFile function. This is what the createFile function looks like. And it's a generic function, like I said. It's about creating a file object behind the scenes that's going to point to some device, which could be a file in the file system, but could be something completely different. So we need to use that. So let's go ahead and do that at this point. We know that we want to access our driver. So we need to be able to call the createFile function. and provide appropriate parameters. And the first one is that finding, which is in fact a symbolic link. What would that symbolic link look like? So first we need to provide these prefix of 2 backslashes, a dot and a backslash, and I need to double each one of those because we're looking at a C or C++ string, and the backslash has a special role here. It's an escape character, so we have to double all of those just to make the compiler happy with what we want to do. And then we need to provide some kind of name. Now, what should that name be? It really depends on the driver. The driver is the one that's going to register that symbolic link. But since we're going to be writing both sides, we can decide whatever we want. Let's call that proc access just as a good enough name. As long as it doesn't collide with other names as symbolic links go, then it should be good enough. And then we have the other parameters we have to provide here, such as generic read, generic write. We might need to read or perhaps write data to that device. Then we have sharing, which we don't really care about. It only makes sense for actual files in the file system. We don't care about security here. We're opening a handle to an existing device. The important thing is to use the open existing flag here. This is necessary for devices. And then we have some flags we don't care about and something called template file, which we don't care about either. So if that doesn't work, in this case, the invalid handle value is the value that is returned. It's actually equal to -1. This is one of the only, I think the only function that returns -1 on failure. All other create functions like, or open functions like create process, open process, things like that, return null on failure. And there's actually a reason for that, which is not important at this point. But in this case, let me just write error opening device and display whatever get last error has to return. In this case, we're done. There's nothing we can do. Since we are unable to open a handle to the device, then there's no way to talk to the driver, which means we're really nothing else to do. So now that we have a handle to the device, we can move to the next step. So the next step is really talking to the device in some specific API, like read file, write file, or device side control. And so the question is, what should we use? And I'm going to talk about the environment in a moment, but in general, we have these 3 options. And again, it depends on how the driver is expecting us to talk to it. And since we're going to be writing the driver side as well, then obviously we're in control here. We can decide whatever we want. And so the thing is that we want to give the driver a process ID. We should get back a handle. So read file and write file are really inappropriate for that because they only allow one-way communication, either read something from the device or write something to the device. But in this case, we want to do both things. And so the way to do that is use the function device IO control, which is the more generic function where we can specify some input buffer and get back something in an output buffer. That's going to be the thing we'd like to use here. So I'm going to provide the handle to the device. And then we have another thing we can control called the control code. And the purpose of the control code is to be able to tell the driver what do we want that driver to do right now. Because it's possible to ask the driver to do many things if we implement those things on the driver's side. So using this control code allows us to specify what we would like to do right now. What are we asking of the driver at this point? So this should be some kind of number, and I'll talk about that number when we write that on the driver's side. For now, let's just write something like this. Let's call that ioctl open process. And so we'll have to define that somewhere, but the driver is going to do that a bit later. For now, let's just use this constant and assume that it's defined somehow. Then we need to provide the input buffer. What do we want to give the driver? We want to give it the process ID. So here's the process ID. We got that from the user on the command line. And then we want to get back a handle. So we're going to provide the address of that H process, which has the value of null right now. But after the driver is able to do its work, maybe it would have a different value, which is what we're after. And then there's a parameter indicating how many bytes we receive back, and some structure, which is for asynchronous I/O, which is unimportant here. We're just going to define ret here. So if that works, then in fact, we're going to get a proper handle and we're done. So then we can call these DLLs here and everything is just fine. Otherwise, we'll fail and we'll get the error here. And of course, it's a nice thing to close the handle to the device, but I'm not going to bother with that for now. And that is essentially it. That's all there is that we really have to do on the client side. At this point, it will not compile because of that value, which we don't have just yet. But once we have that value, the client will compile just fine. Of course, we'll have to now implement the driver side for all these things to have a chance of succeeding. But at least we know what the expectations are from the client side, which I think is more convenient to start with instead of starting with the driver, because we know what the client needs, and then we'll implement that on the driver's side. So let me give you a brief introduction to how to build drivers in general. Now, if you're familiar with Visual Studio, building drivers these days is actually very similar to building other kinds of applications. You just need to start with a different project template and use, of course, a different API. And so you can use Visual Studio 2022 and then you need to install the Windows 11 SDK. Usually you should go with the latest one, and then the Windows 11 driver kit. Note that it's not really about the Windows 11 operating system per se. You can install that on Windows 10 as well. It's just the SDK and the WDK providing the headers and the libraries that you need. And these latest versions they support building drivers for Windows 10 and later only. If you want to build drivers for earlier versions like Windows 7, Windows 8.1 or something like that, you have to use Visual Studio 2019 with an earlier WDK that supports that. And then, of course, you might want to install WinDebug as a kernel debugger, because unless you're writing without bugs, you probably are going to need to debug code at some point. So once you have that, you get some project templates within Visual Studio, and then you can write your driver, or at least start writing the driver. And the basic thing is when writing drivers is that you need to use a different API. If you're familiar with the user mode APIs, that's great, but the kernel has its own API, which is documented, at least part of that is documented in the Windows driver kit documentation, or you can find that online. And so you have to learn a new API. There's really no way around that. But it's not just that. You also have to learn a few important concepts which are not the same as, or sometimes don't even exist in user mode at all. So we have kernel APIs, and at least in the sense of design, the kernel API is better designed than the user mode APIs, which have a very long history, starting from the old Windows 3 version and so on. And so what you find is that most kernel APIs have these prefixes. These prefixes should give you a hint as to what component or part of the kernel this API is part of. So if you have something starting with OB, you know it's part of the object manager. If it's something starting with IO, you know it's part of the IO manager. So it's a bit easier to get around the kernel API, but still there's a lot to learn there. Let me start with that. So in general, let's just create a new project to build our driver. I'm going to right-click the solution, use add new project here to add another project to the solution. I'm going to use this template called empty WDM driver. We'll use that. That's kind of the most basic template you can start with. There are others which are providing perhaps a bit more code, but they're not really relevant for what we're trying to do here. And so it is an empty driver, at least almost. Let's call that the proc access. And you'll notice that this project is empty, or at least almost empty. We actually have an INF file here being generated by the wizard. And this INF file can be used to install this driver. So although it is possible, and in many cases, in fact, it is mandatory to use an INF file to install a driver, for a particular driver we're writing, it's not really necessary. You can use other mechanisms to install the driver, and we don't want that extra dependency, so I'm just going to delete that. It's important to remove that from the project, otherwise you find that it won't compile successfully. So at this point, we have a truly empty project. However, we do have the correct settings for the compiler and linker for building a driver. And that was the point here. It's not really the files, it's actually the settings of the compiler and linker. So let's add a new item here, a C++ source file we can use. Let's call that proc access. We have something to get started with. And the first thing we're going to do is add an include to ntddk.h. This is the main header file you typically include when writing drivers. That's kind of like the equivalent of Windows.h on the user mode side. You get most of the kernel APIs in this header. And then you need to start writing your driver. And so let me give you a few more details about drivers before we actually start writing the code. So first, the return value of most kernel APIs is called anti-status. This is just a 32-bit number that indicates success or failure. 0 means success. This is known as status success. And then negative values indicate some kind of failure. And of course, there are many kinds of failures that are available in the Windows WDK headers. If that kind of status is somehow returned to user mode, it gets translated to an error underscore something that is known to user mode APIs. So that's something to know. Now, when we are using APIs and want to check whether they succeed or not, we use typically the ND-success macro, which simply looks at the most significant bit to indicate whether we're talking about a successful or failure status, and that is it. We don't usually care about the specifics of the failure if it is, in fact, a failure. So what is a driver? As I mentioned, a driver is just a bunch of functions. And so one function that we'll write is driver entry. This is a mandatory function in every driver. You can't create a driver without driver entry. That's like the main function of a driver. This is going to be called when the driver is loaded by the kernel. This is where the driver can initialize itself and export other entry points that the kernel should know about. And there are other callbacks or entry points the driver can provide. We'll focus on just driver entry and something called the dispatch routines. Dispatch routines is an array of function pointers that can be pointed to things like a read file, write file, device side controls. What happens if these kinds of APIs are being called by clients, which functions should be called by the driver. So we just need to specify those that we support. Anything we don't support already has a built-in kernel function there that's going to say to the client, this is not implemented or not supported. And there are other callbacks we can use in a more complex driver like interrupt service routines and DPC routines. This is way beyond the scope of this talk. We'll just need the driver entry and a dispatch routine for our device side control handling. So really, what is a driver? Just a bunch of functions. It's just a matter of telling the kernel what we support so we get called in the appropriate time when these kinds of requests are coming in from clients or certain callbacks we might have registered by using the kernel APIs. So let's look at strings just to give you a sense of what that looks like. You may be familiar with the simple C-style strings that are just a pointer to a bunch of characters ending in a null terminator. Now, the kernel uses strings differently. It uses something called the Unicode string, which is like a Unicode string descriptor. It actually points to a bunch of characters and has a length member that indicates the actual number of bytes this string is occupying. This means the string doesn't have to be null terminated. In most cases, it is not. So you should never assume these kinds of strings are null terminated. And so there are a bunch of APIs to work with these kinds of strings, just to let you know that when you encounter strings in the kernel, typically that will be a Unicode string structure rather than just pure C-style strings ending in a null terminator. This is not the way the kernel works. And it's definitely better because you have the length, you don't have to traverse the string, and it means you can even have embedded nulls within the string, and it's perfectly legitimate and fine, and sometimes, in fact, useful. So we'll see one or two APIs using strings once we start writing some code. So here's the beginning of what we want to do. We have to write a driver entry function. And driver entry has a certain prototype which we have to use. And this is what that looks like. So let me go ahead and add that to our code. So we have anti-status here. This is what we have to return. This indicates whether the driver was able to successfully initialize itself. If not, if we return a failure status, the kernel will unload our driver. What we get here is a pointer to something called the driver object, which is an object representing our driver. It's created by the kernel, partially initialized, and then it's passed to us for further initialization. And then we also get a Unicode string pointer here, typically called registry path, which is the one that points to where the driver is registered in the system registry. And that location is shown here. It's HQ local machine, system, current control set, services, and a particular driver name that is being provided as part of installing the driver, which we'll do, of course, later on. Why do we get this path? Simply as a convenience, because sometimes drivers might want to store configuration information in the registry, so we already get a Unicode string pointing to that location, and essentially we're kind of good to go. So we may need to use that, not in this driver, but in other more complex drivers that might be useful. So here's where we have our driver entry function. What can we do here? One thing I can do is add something. Let's use dbg print here, a simple function to add some formatted strings to be able to see in tools. So I can say something like proc access and driver entry, just to indicate that we're here. In fact, I can also display perhaps the driver object pointer here. So I can do something like this. Let's return here status success for now. So dbg print is like a printf style of printing something, which certain tools can capture. So let's see if we can compile that. So I'm going to use build here to compile that. And what we get here is a warning saying that registry path hasn't been used. So this is a warning, and that's because the default settings set the warning level to level 4, which is the most strict. So every little thing that the compiler doesn't like, it's going to report. And in addition, there's this setting that is set by default, indicating that warnings are treated as errors, which means if you have at least one warning, the compilation will fail. And this is what we get. Now, of course, we can turn this off, but it's actually a good thing. Usually, warnings is something you want to take a look at because they might hide bugs in disguise. And so we don't use registry path, so how can we get around that? One option is to use this macro called unreferenced parameter. So what unreferenced parameter does actually references the variable just by placing it with a semicolon, and that is it. And the compiler will be happy with that. So that's one way of doing that. The other way, because we're using C++ here, we can simply remove this name, and that would be okay as well. So let's try it again right now. And you can see that we still get failure, but this time the failure is actually in linking and not in the actual compilation. So we have a linker error, not a compiler error. And the reason that driver entry has to be exported as a C-style function, and since we're using C++ here, we have to tell the compiler that we'd like to export this function as a C function rather than C++ function, so it doesn't get any kind of name magnet that some of you might be familiar with. And now it's all good. The driver is compiled and linked successfully. We have a C file. Of course, the driver is kind of useless at this point, but at least we have something that compiles. We still don't get proper compilation in the user mode application because of that missing IO control code, but we'll get to that very soon. Okay, so we have driver entry here, and now we can go ahead and do the initialization here. So I'm just going to work on the code, and I'll talk about some of the theoretical aspects a bit later once we finish working on the code. So what do we need to do here? Driver entry runs, that's great, but now we need to tell the kernel about other stuff we support. So I'm going to use driver object here, and the one thing we need to provide is called driver unload. Driver unload is a pointer that needs to point to a function that's going to be running when the drivers unload. This is a cleanup function. It's exactly the opposite of driver entry. Let's call that on unload, and I'm going to write it here. It has in a particular prototype we have to add here, but I'm just going to do the right thing. So it actually returns nothing and gets a driver object here. We might need to use. That's what we get in the unload function. The second thing that we need is to fill up the stuff in the major function array. This is a bunch of indices pointing to functions that need to be called when certain requests are coming in from clients. This major function is a big array. And so we need to actually support three things here. One of them is IRP-MJ create. It's just an index. If I press F12 here, you can see here all the list of the major function calls that are supported, things that the driver can support. There's a big list here. What we need to support here is create. That is necessary because this is what's going to be called by the create file call from the client. If you don't support that, create file will fail. And obviously, we won't get anywhere. The opposite of that is close. This is really the close handle call. Then we also want to support a device side control. So we have IRP-MJ device control exactly for this purpose. If you wanted to support read or write, would use these indices. In this case, we don't. So going back here, we need to use the IRP-MJ create here. I'm going to use the close here as well and point to the same location, because we actually just need to say that we agree. We have to agree, because if we don't agree, the functionality will automatically fail and create file will never work, so we won't be able to talk to the driver. So we need this onCreateClose function, which we'll have to write. And then the other thing, which is the most important thing that we're doing all this work for, is the major function for IRP-MJ device control. This is going to be called for a device I control call. Let's call that on device control. Of course, they also have to have a certain prototype, so let's do that. So we have on create close, and this, since this is an array, they all have the same prototype. The first parameter is something called the device object, which we'll get to very soon. And the second thing is the IRP. That's the actual request itself. So we have that, and we have on device control. We have to implement all that stuff. Before we do that, we need to continue by creating a device object, which is a way to communicate with the driver. In fact, we open handles to devices, never to actual drivers. So we need to have some kind of device name, and then also a symbolic link pointing to that device. So how do we do that? The way to do that is to use a function called IOCreateDevice. So IOCreateDevice would create a device object. This is necessary. And then we'll create a symbolic link that would allow user mode clients to contact indirectly that device object. And so here, let me give you another example here, just to make it perhaps a bit more concrete. Here's the Process Explorer tool that many of you are probably familiar with. Now, Process Explorer, when it is launched with administrative privileges, it also has a kernel driver. It has a kernel driver that it uses to ask it to do certain things, such as the ability to see DLLs in protected process, which Process Explorer now can do for version 17. In fact, I added that functionality a few years back, and it can only be done because the driver is now able to provide that functionality. So if we look at the symbolic links here, we'll see there's a symbolic link called ProcEXP152. This is a symbolic link created by the Process Explorer driver, which is pointing to a device object under the device directory here, which also has the name ProcEXP152. That's the device object created by the Process Explorer driver. So we need to do something very similar. Again, Process Explorer doesn't access hardware. It uses a virtual device in that sense that it doesn't talk to any kind of hardware, simply to have a connection, communication endpoint, something to talk to. And so we need to create something similar, create a device object and a symbolic link. That's the idea here. So there's a question here. By default, Windows allows process VM read, which seems to read access to process memory. So process VM read allows us to read the address space of a process. That is correct, but you don't get that for certain processes. For some processes you do, especially processes created by your own user. Usually you have full access to those without any issues unless they're specifically protected by some other entity. But yes, other than that, you can do that. And there are many other access masks you can use. So yeah, there's no user confirmation here. It's just either you get that access or you don't. In this case, I have access to Explorer without any issues with process VM read. But as you can see, for CSRSS, for example, I don't have an appropriate access. Even if I would run with admin privileges, I wouldn't be able to do that. So it really depends on the power that you have or the process that tries to make the access has. So what we want to do here, going back to where we left off, is to create a device object and a symbolic link. So let's see what IOCreateDevice wants. The first thing is the driver object pointer, because the device is connected to the driver. In fact, it's stored in a list that is maintained by the driver object. Then there's something called an extension size, which allows us to allocate extra memory for use on the device, but we don't really need that in this case. And then we need to provide a device name. So this is where we have to use Unicode string here. Let's call that dev name. So you need to provide a name in the device directory. So we're going to use RTL Unicode string. This is one of the functions that allows us to initialize Unicode string based on a C-style string. I'm going to use that. It's a simple function. And then let's create something called device. Let's call that proc access, which is a reasonable name. So now we can provide this name here as part of our create device. And then there's the device type. The device type, it doesn't really matter for custom devices. We just need to provide something like file device unknown, just a constant. Nobody really cares. Then we have some flags, which we don't care about here. And then whether the device is exclusive or not, whether we can open multiple handles, multiple file objects to the same device. There's no reason to prevent that. I'm going to make it a non-exclusive device. And then finally, we have the result. The result is actually the last argument here. So we need to provide a device object pointer here and then pass the address of that pointer to get the result. And so what the kernel does here, it creates a device object by allocating memory in kernel space and then brings us that pointer back. Of course, it performs some initialization on the device object. Now, if this fails, so we have some error here. So we can use something like dbg print here to display the error, for example. We can say something like error creating a device and even get the actual status here. But regardless, there's really no point in continuing. We can't really move forward. We have to return that status and we're done because we can't create the device. It fails for whatever reason. It shouldn't really fail, but maybe the device name already exists or something like that. Maybe we're out of memory, things of that sort. If that happens, there's really nothing for us to do except report that failure back to the I/O system, which will then unload the driver. If that works, we need to do the second thing, which is to create a symbolic link. And for that, we need to call another function. That's also a fairly simple one to use, much simpler than what we've seen now, which is IO create a symbolic link. So that's the function. And it says, give me a Unicode string that represents symbolic link. Give me a Unicode string that represents the device to connect to, and I will connect both of these. So we have another Unicode string here that we need. Let's use that. Let's call that symlink. Let me make another call to RTL init Unicode string for simplicity. And we'll give it some name. Now, the important thing is to put it in the 2 question marks directory, which is where the symbolic links live. Then we can give it any name that we want, but in this case, the name is important. It has to match exactly what user mode is expecting. So this proc access has to be the same as the string used here. That's a symbolic link name. So these have to be the same. They have to match. It can be anything I want, but they have to match because that's the way to get the proper access to the device in question. So we're going to have symlink here and the device name, which we already have. So this returns the status again. If that fails, for whatever reason, then we need to return the status. But in fact, there's some other thing we have to do here, which is to undo what we've done so far, which is to delete the device. So these subtleties are not really important for this session, but just know that we have to clean up after ourselves, because if we don't do that, nobody will. And the next time it's going to be cleaned up only when we restart the system. And kernel components never get cleaned up automatically. It's the responsibility of the driver to make sure it cleans up after itself. Otherwise, you're going to leak something until the next restart. Once we get here, we're done. Everything is, we're done, at least from a driver entry perspective. We have everything that we need. We have a symbolic link. We have a device object. We're good to go. So if I build that, it should compile, but it fails to link, of course, because we're missing implementing these functions. So let's start with on-unload, which is the simplest to use. On-unload is really supposed to do the opposite of what we've done in driver entry. So one thing that we have is the symbolic link. We have to delete that. So here's the symbolic link. Let's call IODelete symbolic link. That's one thing. We have the symlink to delete. And then we need to destroy the device object. And that's kind of tricky because we have a pointer to a driver object, but where is the device object? It's not here. How can we get access to the device object? So one way of doing that, perhaps, is just putting this device object as a global variable, for example. That would definitely work, but it's not really necessary. And that's because if we go here, for example, we can see that in fact what happens is that when we create a device object, it's going to be pointed to by the driver object. If we create more device objects, which in these cases are not useful, but in other drivers might be useful, we get a linked list here. So in fact, the first device object is pointed to by the driver object. And what we need to do is simply go ahead and access that. So let's do that. So we have IO_delete device here. And in the driver object, there's a pointer called device object. That's pointing to the first device object, which is in this case is also the only one. So that's all there is to it. We have an unload here. We can even add another print here just to indicate that proc access is being unloaded. Just so we can see something in tools, just to make sure everything works as we expect. Okay, so good. Now we have that implemented. We're missing two functions here: onCreateClose and onDeviceControl. So let's start with onCreateClose, which is the simplest of the two. What we get here is the device object, which we don't care about because there's only one and we know what that is. And what we do care about is the IRP. That's the data structure representing the request itself. Now, in this case, the only thing we need to do is to say we agree. We agree that the create file and close handle calls will succeed. So the way to do that is to complete the IRP successfully done in the following way. The IRP has a status, so we have to provide the status indicating success. I'm going to say this is going to be completed successfully. And then there's also a member here called information, which provides extra information for certain types of requests. In this case, there's no special information. And then the actual function to complete the IRP is called IOCompleteRequest, where we provide the IRP and something which is related to a priority boost, which we don't care about. And then we just return status success. That's it. We have create_close working for us. Okay, what else? Now we have the final bit, which is the most important one. In fact, we did a lot of work here just to get to that device IO control call. This is where we get the input buffer. This is where we're supposed to provide an output buffer to the client with the appropriate handle. That's why we're doing all this stuff that we're trying to do here. So in fact, that's the most important function. So what do we get here? We get an IRP, as usual, that wraps the information there. So we have the control code there, for example. Let's see if I have a slide here to bring you some more clarity here. So this is what the IRP looks like in general. You can see there's the IO status structure here containing status information, but in fact, some of the information is provided in an adjacent structure called IO stack location, which follows the main IRP. The reason for that is not something I can get into here, but just let's just stick with the fact that we have one of those. So in fact, we have one IRP and one IO stack location, and some of the important information is actually stored in the IO stack location, such as the parameters of the request. So in that IO stack location, there's a big union called parameters that has a bunch of structures, each one representing information for one kind of request. In this case, we have device IO control, which we're interested in. So given the IRP, we can get to the IO stack location by using an API, and then we can look at device IO control. So let's do that. I know I'm moving pretty fast, there's just no way around it, but you can watch that later on, perhaps again, maybe in half the speed, and it might make more sense, I hope. Okay, so first we need the IO stack location. Let's grab that by using IO_get_current_IRP stack location. That's the API to use here. I'm going to give it the IRP. I'm going to get the IO stack location back, which is a pointer to an IO stack location. Let me just spell that out explicitly without using the C++ auto keyword to make it a bit more concrete. And then what we need here is the stuff within the parameters there. So we have IRP SP here, and then we have here the parameters union, and then we have device IO control. So this is a structure that contains the details for the IO control that we're going to get here, and some details about the buffers. So in fact, if we look at what we have here, one of these things here is the IO control code. This is where the IO control code is provided. and we might support multiple control code in our driver. In this case, we're going to support just one, but in a general case, we might be supporting multiple ones. So we need to look at the control code here. I'm also going to start with the status here, called status invalid device request, some kind of failure status. And so what happens that if we get the control code that we expect, called ioctl open process, which we have yet to define, then we'll do something with it. Otherwise, we'll fall through here and complete the request with whatever status we have. So I can go ahead and copy this code here, because completing the IRP is essentially the same thing, just need to change the status here and return whatever status we have available at this point. So if the control code is bad, something we don't support, then we'll fall through here and complete it with this status indicating there's some kind of request we're not aware of, we don't know how to deal with that. So that's almost all that we need here. Okay, so the next step is to define this control code. How do you define that? So I'm going to add another header file. I'm going to add a header file, in fact, to this driver project. Let's call that proc access public. The idea here is that this header file should be shared by user mode client and the kernel driver, because both need to know about the control code. So we need to define this control code here. So let's go with ioctl open process, seems like a good enough idea here. So we want to open a handle to this process, and that's the control code that's going to be defined here. Now, you might be thinking you can just use some kind of random value like 1 or something like that, but no. In fact, we have to use a particular macro called control code to build the value as comprising of these 4 parameters I'll show you momentarily, because some of these parameters actually affect how the buffers from the client reach the driver. So here's what that looks like. The first parameter is called the device type, which could be anything, but the documentation says please start with 8000 hex. And then we have something called the function number, which could be, again, anything, but the documentation says that Microsoft reserves all the values below 800 hex. Okay, fine. The important parameter is the third one. It indicates how the buffers from user mode reach the kernel. And I won't have time to explain exactly what it actually does, but we have to use something so that we can get the buffer that the client providing. In fact, it provides 2 buffers in our driver in a particular member within the IRP. So for now, I'm just going to just use that as something we need to know. So once we have that, file any access means that we can use this control code to read and write information, which is important in this case because we get something, we also return something back. We get the process ID, we return a proper handle. That's what we want to do. And if I go back to my client application here and add an include for that public header file, now the client application will compile. So the client application now knows what that is and can use this number, but of course we have not yet implemented that on the driver side. So we need to add that as well here. So let's add the proc access public here, so we'll be able to access that IO control code, and then if we get that control code, we want to do something. If we don't, obviously we don't want to do anything and just fall through. Okay, so what do we need to do here? We need to do some checks. So let's say, see, if the input buffer length is smaller than 4 bytes, which means we don't have buffer which is big enough, or the output buffer length is too small to accommodate a handle, or let's just add this here as well. We have the IRP. System buffer is where, associated IRP.system buffer, this is where we actually get the user's buffer. So if this is null, that's bad. So all these things are bad. We can just do something like status invalid parameter here. It's critical in real drivers to check errors, because otherwise we might blue screen the system. You don't want to get into that position. So if you get bad input from clients, and you never should trust clients, you should make all the necessary checks. Otherwise, you're risking blue screen the system. So now that we have these checks out of the way, we know the buffers are big enough. We know that we have a pointer which is not null. It's time to get the input value, which is in fact our process ID. So we have the process ID here. Let's just grab it from the buffer. I'm going to treat this buffer as an int pointer to get the actual process ID here, just by referencing it. We know that it's there. Maybe it's a garbage process ID, of course, but at least we know there is something there. And then we can go ahead and do the work. So what we want to do here is do open process. So the client here did open process, but with the powers of user mode. We want to do open process with the powers of kernel mode. And for that, we can use the function ZW open process. That's the function that's going to allow us to open a handle to any process with any access without restrictions. Okay, so let's see. The first parameter, so of course, we have the status here, because this thing could fail, of course. Maybe the process is just a garbage ID, it doesn't really represent any kind of process. So here's where the result is going to land. That's the first parameter, in fact, it pointed to the handle where the result is going to land. The access that we want is process all access. Let's give the client everything, no restrictions. Object attribute is a data structure we have to create here. It's not really important here, but we still have to provide this. And so we're going to call initialize object attributes. Usually it's used to provide some kind of settings, flags, or names. In this case, there is no name. Initialize, if I'm able to write correctly, but we do have to provide something. And the important point here is to provide a value of 0 for this flag, indicating I want the handle that's going to be returned from this W open process to be a user mode handle, rather than a kernel handle, which will not be able to be used by user mode. So I'm just going to initialize that and provide the attributes here. And then we have the last parameter, which is the client ID. This is where the process ID should be specified. This client ID thing provides a process ID and a thread ID. In this case, we just need a process ID, and the thread ID has to be null, 0. So here's where we need to provide this PID that we got from the client. But there's a slight hitch here because unique process is actually of type handle, but it is in fact an ID. And the reason is that process and thread IDs in the kernel are actually generated from a private handle table. So it's not really a handle. We just need to cast it for the compiler to be happy. We can do something like ulong to handle, a function that is provided to make the compiler happy. And now we can provide the client ID here. Okay, so if this fails, maybe it's a garbage process ID, there's nothing to do. Otherwise, we're done. We have a handle, we just need to put that in the buffer of the client, which is in fact the same exact location. So you can do something like this. There's one way of doing that. We can also use memcopy if you prefer. It doesn't really matter. Memcopy also exists in the kernel, by the way. So we have IRP, system buffer. We need to copy the handle here. And size of H process. And we're almost done. Of course, the status is success. It's all good. The only thing left to do here is to indicate to the client that really we have some buffer here with some size. So we did return something in the output buffer. It has to be provided in this information member. So I'm going to go here and initialize that to 0. But if all goes well, we'll get that set to the size of handle here. So that, in fact, we'll be able to return proper handle to the client. And technically, we're done. That's it. The driver is done. Of course, it just built. It doesn't mean it actually works. So hopefully, we'll be able to make that work. So let's try. So let's go to Explorer here. And I want to test that on a virtual machine. So I have here my output folder here. We can see we have the driver. We also have the client. Let's grab both of them. I have a VM here. I'm going to paste it here. So we have these two files here. Now, the first thing I need to do is to install the driver. Now, installing a driver could be done with an INF file, but we're going to use a different scheme using the same scheme as we use to install services. In fact, drivers can be installed in services, at least these kinds of drivers. So I'm going to use the SC tool, which behind the scenes would call the create service API for those that are familiar. So let's call that proc access. This is just the name of the registry key that's going to appear once we install the driver. We need to provide two parameters here. The first one is the fact this is a kernel driver, not a service. And then we need to provide the path to the driver. That's going to be e demo and proc access.sys. And it says create service success. Of course, we have to do that with an administrative command window because installing a driver is a privileged operation. And by default, administrators can do that, but normal users cannot, which makes sense, of course. And now that we have the driver installed, in fact, we can open the registry just to verify. Let me go to the registry editor here. If we go to HK local machine system current control set services, we'll be able to see that proc access is here. Where is it? So proc access, crappy editor. Okay, so proc access, you can see here the path to edemo proc access.sys, and type equals 1 means that this is a kernel driver, and start equals 3, that's the default, means that it's starting on demand, only when we ask it to start. So at this point, if I open WinObj, which I think I have here on this machine as well, if I go to the question marks and I try to look for something like a proc access, I will not find it because the driver is not up just yet. It's not running just yet. So we need to run it. And I'm also going to use a tool called debug view from sysinternals to allow us to look at output coming from kernel drivers, kernel in general. So we should be able to see our output if everything goes as planned. Okay, so now we can start our driver. Even before we do that, let's go ahead and open another command window here. And let's go to edemo here. So we have our list DLLs. We need to provide some process ID. So at this point, if we again open Task Manager in this virtual machine and look for something that we can access, probably like Explorer, that shouldn't be a problem. So 4564. If I do that, we get a list of DLLs, not a problem. But if I go ahead and ask for something which is protected, like a CSR SAS process, like 876 here, let's try that. Here's what we get. We get an error, and the error is it's trying to open a device, our device, but it can't find it. Error number 2 is find not found, essentially device name not found, because the driver is not up yet and it won't be able to contact it. So then let's now start it by using the scstart command. So we're going to use scstart with the name of the registry key, which is just proc access. And we'll see if we get a blue screen or not. So no blue screen, I guess that's something. Notice proc access just appeared. So you can see that the symbolic link is here, pointing to exactly what we wanted here. In fact, you can see the output that indeed driver entry was called, and that's our driver object address. Notice it's a big address. It's in the upper 128 terabytes of address space, which is where the kernel is. So at least the driver is running, so that's something. Now we can try our code here. Again, going back to my other command window here, I want to try listing whatever is in CSRSS. And now it works. You can see it works because we're able to open a handle to the process by utilizing the power of the driver. And now we see exactly what's in any process that you wish. Any protected process is fully visible now. There is no limitation here. So CSRSS is one example. You can use something like SMSS, the session manager, 676. We can try that. And it works. So let me summarize some of these things because I've probably missed a few details here while talking. So I talked about dispatch routines and talked about the various IRP types that we've used. We've used just create, close, and device control. That's all we needed for this particular simple driver. This is how we complete a request. We've seen that. And then I talked about installation. So we need to install the driver. We have to do that from an elevated command window. We can do that in this way. Now, you might be wondering how come the driver was actually started successfully, because drivers need to be signed. And I didn't sign my driver. And the reason that my system was in a test signing mode, which means I can run or load drivers which are not really signed. That's why it worked. If you look at the virtual machine here, you can see here on the right, it says test mode. And test mode means that test signing mode is on, which means I can load drivers which are not signed. So that's something I did beforehand. This can be done by using a command line, which I think I'm showing right here. So if you use bcd-edit/set test signing on and restart the system, you're going to put the system in test signing mode, and which means that you can test drivers without having to have a proper signature. And that's what I've been doing here for, of course, demonstration purposes. Of course, once you want to actually publish the driver, you probably want to sign that, so we'll be able to load on normal systems. So I hope this makes sense. I know this was a very fast and, well, super fast way of showing you how to write a driver and the client application. The client application might be easier to understand, but we looked at both of these sort of sides of the equation or sides of the red line, separating user mode from kernel mode. If you have questions, feel free to ask. If you kind of have the enough, I would say, power to ask these things. And of course, you can reach me later on using various locations in Twitter or LinkedIn or even YouTube to ask things if you want. And if you're interested in a full-blown kernel course, then you can definitely look at my course in trainingsec.net. Thank you.
So, well, thank you, Pavel. Thank you so much for such hugely insightful webinar. And as I can see, you already answered the question about processing and read, and I think there's no other questions for now. I see that some people wrote that they are huge fans of your books. Yeah, dear audience, if you have any further questions, you will have a chance to ask them offline on the main day of the DMZCon conference on the 2nd of October. Save the date in the calendar not to miss it. And just a reminder, you can attend the conference both online and offline too. And whatever your choice is, you'll see and get in touch with really big figures from the world of cybersecurity as Pavel Yosifovich. Yeah. Thanks a lot. Thank you for being with us today. And I think
thank you.
Yeah, we are ready for now, and follow us on LinkedIn to stay tuned with more conference updates. See you this Tuesday for the next webinar.